Howdy, everybody. How's your Wednesday going? Going all right? All right. Let's see. To start off with, I'm recording, so I'm going to record tonight, and I might review a little bit because I thought I was recording, or I set the recording and it didn't record fully. So I might do a little bit of a review tonight, and then talk about the assignment, and then the deliverables for project 2. So this is a good session to sit in on, okay? All right, so let's get started. First thing here is, let me pull up my outline for you guys. I need to share my screen. All right, can you see the screen? You should see July 13th office hours. Thank you, Hope. Okay, just to set the due dates here, project 2 is going to be due July 19th. I'm going to post the rubric on Friday. I'm going to review the rubric with you today, see if there's any questions, and then post the official rubric on by Friday. That's my goal. And there's a part of this that is a analysis document. So it'll have kind of a writing element to this project. You'll need to be able to document your approach and your algorithm and show a table of some results that you've performed on your own images. So we'll cover that. And today I'm going to give you an introduction to the algorithm for asymmetry and border on the mole versus melanoma projects. We'll do that today. Okay, so that's the outline for today. Okay, let's work a little bit in reverse. And meaning that I'm going to show you the project 2 rubric and talk about it. And then I'll give you some hints on the algorithm for asymmetry and border. All right, so let me pull that out. Okay, so similar to the last project, there is going to be let me see if I can zoom in a little bit for you. That's a little bit easier to see. There's going to be a code organization and documentation and style, total of 7 points, 7 different prompts. Once again, reusable code, works on new images, and you've got external functions and doc streams, help that's documented, section of code clearly marked in the beginning of the main program that includes defined constants, path to your images, the threshold constant, and other important constants. Your code has been visually organized, kind of import sections, and then the application defined constants, and then the major section of your code is clearly defined. Flowchart and pseudocode will be for your asymmetry algorithm will be required. On Friday, we will meet as a team and you will work on your pseudocode and flowchart. So that'd be a good session for you to attend. Okay, so there is an analysis documentation that's required for this project as well. So for the analysis documentation, it's kind of good to show you an example of what I'm looking for here. And let me see if I've got one. I think this is a past student's work that I thought was really good. Project 2, mole and melanoma, excuse me. Project 2, mole and melanoma analysis document. Gives an overview of the asymmetry test and talks a little bit about the thresholds for when you're deciding that asymmetry is at risk. Okay, same thing for the border test, same thing for the color test. So give the logic of when you're going to assign either a green, yellow, or red based on these criteria. How is it symmetric or asymmetric? Is there a jagged border? And then based on, is there a lot of different colors in the lesion itself, the skin lesion? Okay, so this is an example. The student wrote this up. And then how do you take that information and you create a risk analysis? And I'm asking you to rate each of the images of the mole or melanoma with a green, yellow, or red. So it's kind of a qualitative score, but you will use quantitative information about the lesion, the quantitative information being how symmetric is it, and secondly, what is the border jagged or not? So those are the two factors. And the third factor is color, which will be a bonus. Okay, you have 5% bonus on this project. So what this student did is listed out all their test images. So you're required to go find your own test images. I've given you a few test images: mole 1, heart rotated, melanoma 1. You go find your test images, create a algorithm that tests for asymmetry, score these guys, and then score it for the border, which is basically how jagged the border is, and then create a risk level, either green, yellow, or red. So I'm asking you to document each of the test images that you look at, and then how your test images actually impact your algorithm for scoring it red, green, or yellow. Okay, so that's the goal. Here's the summary. And this is without color. This was kind of interesting. The student did it on the test images that I gave the class, and those test images are actually posted at this point. And then they created their own set of test images as well. Okay. So that's a little background about the analysis document. Okay, so that's what this is, and here's the rubric. Probably in critique, this is what I've used in perceptive. I'll probably make this real clear from 1. There'll be different levels. It may not be up to 7. And each of these different components of the rubric will be weighted slightly different. This one is, the code organization is weighted by 1. The analysis documentation is weighted by 1. The outputs is higher rating or higher weighting. So it'll have a weighting of 3. Okay. Code runs to completion is the first prompt. Console outputs are well organized all the way up to code correctly assigns the risk level, red, yellow, or green, to the secret test images. So I'm going to give you the secret test images, which I know are either melanomas or moles, and your algorithm will categorize them. And so you'll be given those test images as a peer reviewer to test against the code from your peer that you're reviewing, okay? And then there's a color bonus worth 5%, and that's based on you've delivered a flowchart. You've given an output risk based on the color. You tested it accurately against the supplied test images. So I'm going to give you some test images for color as well, and you can run that against the bonus and so forth, up to test accurately versus 2 or more of Professor Hanks's test images. Okay, so that's the rubric I'm showing you now, and see if you've got questions or feedback, and then I will post that on critique, and we'll use the same process that we used for project 1. Okay, all right, so you're getting your head around exactly what this project is. Okay, so let me give you a little intro into how to make the algorithm for asymmetry and how to make the algorithm for is it a jagged border or not. Let's cover that next. Let's see. It's here. Okay, by this evening, you guys should have finished project 2, assignment 2, and you are to plot the, let's see, you're supposed to post the area and the perimeter, I believe, of the blob or the lesion. So kind of a little bit of review. Let me do this real quick because didn't record on Monday, and I apologize for that. So project 2, assignment 2, you're given these images and you're perform some processing on these images and make them into binary large objects. And then you'll fill the holes, remove the small objects, and then you will measure the area in pixels of the lesion, which we've turned into a binary object in the image. And then you'll measure the major and minor axis in pixels, and then the orientation, and then the perimeter in pixels. Those are the outputs that you will print to the console. You will use something called SK image measure region props. Region props is very interesting in that it returns the computed value, for example, of the area in pixels of the object that we're analyzing. Okay. Also returns things like the centroid and the perimeter and the length of the major axes. So we'll take an image, convert it into a binary image, and then kind of hard to tell, probably over zoom here, but there are some small holes inside of this binary object. There's a function to fill the holes, remove small holes, and you set a threshold on the size of those, and then it comes back and it's fully connected. You can think of this as a fully connected object. And if we know the number of pixels of this, we're going to say that that's the area in pixels, okay? The next thing that you're going to do is calculate the major and minor axis. And here's an example of the major axis and the minor axis. And then what we want to do is rotate the major axis to be in really a 90-degree up and down vertical position, okay? That's going to be done in assignment 3. You will need to be able to do that, not in assignment 2, but you'll need to be able to return the values for the orientation and major and minor axis in assignment 2. Okay, so this is what it looks like after you've done your processing of the binary image and you've rotated. And the output looks like this. Major axis length, for example, it's 137 on this particular sample. Minor axis, and orientation is -68. Then the area of the objects is 9,450 pixels. Okay, so I've given you a set of images. So here is a made-up mold in the shape of a heart, and you could apply that same algorithm, same processing to this image and recalculate the area, perimeter, and so forth. Okay. All right, so that's what's due tonight. And let me run a little code here to show you a couple of things. Let's show assignment 2 here. And I'm going, in my code, I've got it where I can comment out and I can look at different images. Let's first look at, the mole. Run this. And in this case, I'm going to show the outputs here of the moles, same images over again. So we've got the original image, the grayscale image, and then the binary image shown here. And this is the processed binary image that's shown here. And then finally, the rotated image in figure 5 that I've got. It's been rotated to the vertical. Okay, so if we ran that on the melanoma image, what would that look like? Let's go ahead and run that again. Let me close down these images that I've created here. So I don't have too many images. Okay. And this one's kind of odd looking in that here's the histogram. Those are all of the pixel values from 0 to 1, 0 being black and 1 being white. And then here's what the original image looked like. And then we plotted the histogram after we've converted it into a grayscale. I pointed out that this kind of has an artifact in it. This spike right here is this black bar along the bottom. Okay. Just kind of made this image kind of tricky. And then it's like, what is this? Well, it's a count of all the pixels that are perfectly black, nearly perfectly black in this grayscale image. This, you can see that there's a lot of different colors here. And here's kind of a very dark color. And then this spike here in the image is the background, which is not white, but close to being white. And so each pixel value has a grayscale value. Each pixel coordinate in the image, 0, 0 being the upper left-hand corner. And you can think about the pixels going in X direction and then the Y direction, and this is just one large 2D array. We could assign each pixel a grayscale value from 0 to 1, and these nearly white pixels in the background here is this spike over in the histogram. Okay, if we do our binary processing, the result, if we threshold this, and let's say we threshold this at 0.5, and I've made it clear that all of the images I will give you, you should threshold at 0.5. And so any pixel that is less than 0.5, that's dark in the image, will be assigned a value of 1. And anything that is light or nearly white will be assigned a 0. So we kind of flip the contrast here. So the background is now black, and then the object that we want to process is white, but we end up with all of these kind of artifacts in the object that we want to process. We want to find the area of this thing. So there's a whole set of functions in skimage, the module that I pointed out to you, to be able to kind of connect all those holes so that we can get the area and then process each of the objects, each of the binary objects in the image. And that's called blob analysis. Okay. So if we continue on here and we apply some of the blob analysis functions, we fill in the holes, we're left with, actually, let's call this blob 0, and this is blob 1, and this is blob 2, and this is blob 3. Oh, and the function that's called region properties will return values associated with each of these blobs. Okay, so that's something to appreciate. And if we kind of show some other things that happen here, if we rotate the image, that black bar along the bottom is actually now a white bar, which is hard to see because our background for our graph is actually white. But if we rotate it along the major axis, it shows up here, and now it is a binary large object, and we need to remove that from the image. So you'll have to use some processing to say, remove all of the objects other than the largest area object, which is this guy, and then perform analysis on it. Okay. So let me walk you through the code, how I did all that. First off, let's talk a little bit about the outputs here. So here's the area of the object in pixels. Here's the perimeter. Here's the major axis, the length, and then the orientation. And then I did something called the Y projection and X projection. I'm going to talk about that today, and applied a correlation function to say, oh, the X projection, the left and right side of the image, after it's been rotated, if we correlate them, what's the correlation? And what's the correlation with the top and bottom half of the binary large object? And that's what I've calculated there. It's a little bit easier to show if I use a made up image. So let me just create a simulated image here and we'll apply what I just talked about to a heart. Okay. So let's do that real quick and change my code. Now we're going to apply the same image or same processing to a simulated mole in the form of a heart. Okay, kind of a little bit easier to understand the histogram and the image. It's a made up image. Here's our original image. Oh, the grayscale, it's just a black and white image. It looks exactly the same, but then when we apply the threshold, we make the white values black and then the black values white, it looks like this. Okay, so this is our binary image. And then we process the image and we rotate the major axis along the vertical and it looks like this. Okay. So if we wanted to create an image, create a asymmetry or symmetry algorithm for this particular image, and we wanted to look at the left side versus the right side and the top and the bottom, how would we do that? That becomes the question. And that's going to be what we're going to use for the asymmetry measurement. So when you finish the asymmetry measurement, you're going to come up with a score. It maybe you may in your code go from 0 to 1, for example. 1 being anything above 0.90 could be green, and then anything from 0.7 to 0.9 could be yellow. So that's kind of converting your quantitative measurement into a qualitative measurement. Okay, anything below 0.7 is suspect. So you think about what we're doing here is we're basically giving to the user, giving to the clinician a ranking system that just highlights, oh, you should look at this closely, or the patient should look at it closely. Okay, so that's the concept. Okay, I'm going to stop. I've been talking a lot. See if there's any questions up to this point. Victoria, any questions? Good.
You had said for the rotation, that's not for assignment 2, correct?
I think all I ask you to do is output the orientation. I don't ask you to change the image and rotate it. Okay.
Okay.
Yeah.
And then for the part where when you rotate it, the black line changes to white, is there the SK image a module for that?
Okay, yeah, good question. So let me kind of walk you through the code of what I did here. Okay, so what I did here is this is all just setting up where I can have 3 plots on one graph. Okay, so that's what this code does. And then here's really where I start my processing. So I've already converted the image into a binary image. And let's say if I type binary image over here, can anybody predict what my output should look like? It's a 2D array, Boolean 2D array of 1 or false and true. Okay, we know it's a 2D array because we see the 2 brackets there, and it's a Boolean array because I see falses. Okay, so this is a Boolean array, and so these functions, so this module called morph is coming from SK image morphology. So these are called morphology functions because they're working on the shape of the binary large object or morphology of the binary large object. The first function I implement here is remove the small objects. And what that function does is remove the background, small objects in the background. And there's not any small objects in the simulated image of the heart. And then I set up the values to be the parameters here to be the input image is binary image. It's also the output image. And then the minimum size is 64 pixels, and that's area. Okay. And then the next function I ran was remove small holes. And the remove small holes refers to the holes inside the binary large object. And then once again, I set the parameters of the input, which is binary image, and then the area. Now this function here, let's read about that, really labels all of the binary large objects in the image. We just happen to have one in the simulated image, but in the melanoma image, we had multiple objects that we could analyze. So we could return the centroid of every binary object in the image. For example, if there were 20 objects in that image, we could return the centroid of every one of them, for example. Okay, so that means label those binary objects. And then this particular function is a perimeter. So it's calculate the perimeter. So I gave it my output after my remove small holes, and it calculates the perimeter of the object. Okay. So that's one way to do it. Another interesting way to do it is use this function called region props. Okay, and so if I just said, let's see what props is, it's an object, and I could type out, let's see, just to show you that is an object. It's a list. Let's see, type of props is a list of objects. And in this case, we just have one object in the list. So let me just say props 0, because that's how we would access the first element in a list. And then we see that prop 0 comes back as that single object. So that doesn't look very interesting because we have only one object in the list. So if I did a directory of props, see what that returns. That returns all of the things that we could measure about that particular object. Or I could do directory of props 0. See if that returns. Now here are all of the methods that could be applied to that particular object. Okay. So we've got area. So after I've applied this region props method, it returns this list of objects. And then for each object, I could say I would like to return for 0. Let's say if we just want the area. Okay, so there's the area of binary large object 0. And if we wanted to show the perimeter, we type that in and so forth. Okay. So this is a really powerful method here, this region props, because it gives you all of these properties, including the orientation and perimeter and so forth for the object in the image. Okay. So if we wanted to rotate the image, we get the orientation, and notice that it's returned in radians. So I used a little math here to put it back into angle, 90. There's pi over 2 radians and 90 degrees. And so that returns the angle. And then I basically output the major axis, the length, minor axis, and the orientation. So this is what your goal is for this evening. So now for the next step, for assignment 3, I'm going to rotate this. So I calculate the angle, and I want to rotate it back to the vertical. I had to play around with this to understand it. Is it a positive angle or negative angle? How is it exactly measured? It's measured from the vertical axes. And so if I applied a negative to it and then say transform, which is another module, and rotate, want to rotate the image at that angle and don't resize it. Keep it the same size. So that's another function, another module that you need to know about. So let's go back up here and look at this. And where is it located? There it is, transform, SK image transform. I just called it transform in my code, okay? All right, let's talk about an approach for calculating if a binary large object is actually symmetric or not symmetric. Does anybody have an idea about how we could do that? Anybody?
Sorry, just to clarify for the previous one, like for the melanoma, we should only have at the end one blob that we're analyzing, the binary large object, right?
Yeah, that's a good question. So some of the images you may find on the web that you want to use as your test images may have a couple of let's call them lesions in the image, and I'm going to ask you to just process the largest image, largest object in the image, okay? That'll make it simple.
Okay. Sounds good. Thank you.
So yeah, just process the largest object in the image. So you, for example, you could have 2 moles or 3 moles in one image, and I'm just going to ask you to process the largest one. That'll simplify your program. Okay. All right, you guys are going to have to kind of follow along here. This is, it may take me a couple of times for this to sink in with you, but let me tell you the approach and an approach for calculating the symmetry of an object, okay? So if we rotate this and the major axis is along the vertical, if you think of this as like, I want to check my vertical axis, this axis right here, if I want to check if this side is the same as this side, how would we do that? Well, one method is I can count up all the pixels along this row that are white. And then the first row is 0, right? And I'm now, think of this as a projection. I'm going to project the number of white pixels in each row into a graph. And so here's my projection of this. So as we go along here, we sum all these up and we plot it. It kind of makes more sense if you look at this up. This has got 2 humps, and this side, if we summed up every row and plotted that on this graph, starts out with 0, and then it increases and then decreases, right? It's the number of pixels along each row, each half row, starting from the center of the image. Okay. If we did the same thing along the horizontal here and we projected the top part of the image and counted every pixel along the column, we'd end up with this image that looks like I don't know, a shark fin. And then if we correlated this signal with this signal, the correlation would be very close. It'd be close to 1, right? And so what the correlation function does is outputs a value between -1 and 1. So if 2 objects are correlated, the output is going to be a 1. If they're negatively correlated, you'll have a -1. If they're not correlated at all, if it was just random noise in both of these signals, it would be 0. And so I've got a little example of correlation function that I can show you and give you a little background information on correlation. So let me do that for you real quick. think I have that code up here. Correlation experiments. Okay. If you plotted signal 1, it's increasing up and to the right, right? 1, 2, 3, 4. And if we plotted signal 3, which is 2, 4, 6, 8, you could say that those are positively correlated, right? Because they're both going up and to the right. And then notice signal 2 is going it's going down, right? It's -1, -2, -3, -4, right? So let's print the correlation, and notice that here's the function. It's a NumPy function or method called correlation coefficients. And I'm in this case, let's take signal 1 and we did it up here. Signal 1 and signal 3. Let's start out and say signal 1 and signal 2, and that's going to be the first printout. And then down below we have signal 1 and signal 5. Signal 1. We need to change that to 4 and 5 and print these out. Let's kind of take a look at that, see what it looks like. Notice that signal 1 to itself perfectly correlate. The output is 1.0. And then we've created a random number here, and that the random number correlation is 0. That's what you would expect. It means that there's not correlated at all. They're totally random. Okay, so does anybody have a guess if we correlated signal 1 and signal 3, would they be positively correlated? How close to 1 would it be? Or would it be 0, or would it be -1 correlation? Anybody have a guess at that?
-1.
For signal 1 and signal 3, they're both going up and to the right.
Sorry, I was looking at signal 2. That's my bad. Would it be a 1 since they're
Yes. So it'd be 1. Now notice they're different magnitudes, right? It's 2, 4, 6, 8, and this one's 1, 2, 3, 4. So we plotted those out, right? They would have the same slope, but they would be at a different value. So that would be a 1. So you could play with this. Like if we change this to a 5, and this was to, we'll say that this is not an 8, but a 7, you can go through, and then the value would be not quite a perfect 1 correlation. They're both going up to the right, so it's a 0.94 correlation. So this kind of gives you an intuitive feel for what correlation means. Okay, so and if we took signal 1 to signal 2, you're right, it would be a negative correlation. Let's make sure we don't have an error there. And we can see that it's negatively correlated. And then signal 4 and 5 down below, since they're random, is close to 0. So that's negative correlation, 0 correlation, and correlation of 1. Okay. All right, so I think I even have that in a chart up here. Where did I put it? Nope, I don't have it. I thought I did. Oh, here it is. Correlation is projection axis is up and down. And correlation of projection y-axis is left and right. So it's the top and lower part of the image, and the y-axis is the left and right side. And so you get about a correlation of 1 for the top and bottom, but for the left and right, it's less than 0.6. So would this be a risky mole? Well, that's the whole idea of writing up your documentation. And basically we're going to say, well, if you're correlated along one axis, and not symmetric in another axis, then that's higher risk than symmetric in both axes. So that's the whole goal of this. Is how do we come up with a kind of heuristics or algorithm and document that, and then quantitatively score it and have it match your qualitative risk assessment of green, yellow, or red. All right, so I probably would say that this is a yellow. It's symmetric in one dimension, but it's not symmetric in another dimension. Now notice you could do more than two calculations for symmetry, right? You could go along the diagonal, and if you projected the diagonal and compare the upper left part of the diagonal to the lower right, so you could do many different tests for symmetry around the center point or the centroid of the object. Okay, I just showed you two. Okay, all right, so a question for you guys. Now let's talk about perimeter. If you were to come up with an algorithm for how jagged the border of the skin lesion is, does anybody have kind of a guess or approach that they think we could use for kind of quantifying how jagged the border is? Any inputs on that?
You could compare it to the circumference of a circle with the same area.
Oh, that's a good idea. That's a really good idea. Okay, what Jeffrey has said basically is, let me draw this for you. All right, you come up here and we had a perfect circle, right? And then we had another image that was a perfect circle, but it had all these spikes on it. Let's draw a few spikes. Then like this. And then all the way around, right? So if we did some simple math here and we said, oh, an object that has no spikes on it, if we took, let's say the perimeter, which is, oh, I need to change over to my drawing tool just a second. Yeah, if we said the perimeter is 2 pi r, right, divided by pi r squared, perimeter divided by the area. So this would cancel out, we have 1, this would cancel out. So our ratio for a perfect circle and having no jagged edges would be the ratio of the perimeter to the area, P over A, would be, it's equal to, so this goes to 0 and this is 1, so it's 2 equal to 2 over r. Okay. This guy would have a much higher perimeter. So P over A for a object that has a jagged border is going to be much greater than 2 over r. All right, did you guys follow that? So all we need to measure is the perimeter and the area of the object, and now we have an easy way to tell how jagged the border is. I'll stop there and let you absorb that. Any questions? Okay, let's do this. Clear. Go to the drawings and close this down. Okay. I think I'm going to talk about color imaging on Friday. And I'll send you guys out a note, and then I will post the critique assignment, the rubric for project 2. And you guys on Friday will have the chance to develop your pseudocode, and then you could work on your code for project 2 the next 3 days, and then or 4 days. The project will be due on Tuesday, July 19th. And so you'll integrate all this together. What you'll have to do is go find some of your own test images, okay? So I'm going to give you some test images. And by the way, I've created a tool that creates test images automatically. Let me show you how that works. Here's Python code, and this has been posted under project 2 module on Canvas. And what this code does is actually create simulated moles of different shapes. And you can walk through the code, understand the code. You can change these parameters. And what it does is outputs funky shaped moles. So that doesn't look like a mole, but notice they're at different grayscale values. So you could do your color testing, right? And then here's what that mole would look like. And so you could create your own simulated lesions by using this technique. Oh, by the way, here's what the histogram would look like. And so this, these two dark objects down here are probably this object and this object, which are the objects that have the darkest color in the image, okay? And then this background, this white, is this value right here. So you can download this code and create your own test images. You can go find test images on Google Images. Just search on mole or melanoma, and you'll come back with some test cases, okay? Let's change this up a little bit. Let's change this to 50. We want minimum number of shapes. It would be 3, 2, and then 4. And size of the image. So you can play with this and come up with your own set of simulated images. It looks like I said the minimum size is 60 and the max is 50, so it didn't create anything. So let's change that to 120. Kind of interesting. The random shape that we created was a really large circle and a couple of triangles that were on top of it. Oh, that one would be tough to score. It's got one part that's jagged, so it might get a 2 over R, a little bit higher than 2 over R, but it's pretty symmetric. That one would be tough to score, I think. All right, so that's an intro to project 2, kind of give you the end goal in mind and then work backwards from that. And I've been giving you your assignments that are steps towards solving project 2. I will stop there and see if anybody has questions tonight. And if not, you're free to go. Okay. Melissa, any questions?
No, I'm good. Thank you.
Okay. Hey, Jeff, how's it going? Let me turn off the recording here real quick.